Mojtaba's presentation. Thanks.
Thank you, Marcelo. Before I introduce our eminent speaker, I just want to make a very short announcement. It's more of to source views from people. The Minerals Engineering International Conference, which is held every 2 years, as you all know, it was postponed from taking place in April this year to April next year. Now there is a suggestion that can we just cancel it and focus our energies in organizing the 2022 Comminution Conference. So I just want to get a sense from people if that would be supported so that we can go ahead and make the communique that this conference is cancelled. And then those who would still want to present that material can present in 2022, or those who would like to have it published can do the paper, and we can maybe do a special issue which we can publish, which can be published next year. So I just wanted to get a sense. You can just raise your hand if you support it, so that I can just get a sense of the number of people. Yeah. Okay. Thank you. So I'll communicate, and then you'll see the announcement shortly. Today is a very special day for us. We are going to get a presentation from Mojtaba. He's an eminent professor in chemical engineering at Leeds University. He has many research interests, but in the interest of time, I'll just say he is very much linked to bulk particulate material processing and characterizing the behavior. So he looks at bulk solid material behavior, single particle behavior with aid of simulations. So he's well vested in discrete element methods, computational fluid dynamics, and also application areas of interest include cohesive powder flow and fluidization, size reduction, size enlargement, environmental effects, electrical phenomena, and you can go on and on and on and on. But from this particular audience, it's very interesting that a person who can look at size reduction and enlargement, the two competing areas, can give us a seminar. He is a fellow of the Royal Academy of Engineering, a chartered chemical engineer, and a fellow of the Institute of Chemical Engineers. And until July this year, he was the consultant of the International Fine Particle Research Institute in the size reduction area. And he is the Kona 2019 awardee of the Osokawa Micron Foundation for his contribution to powder technology. So you can see he's got a very large CV. What I've given you is actually just a tip of the iceberg, so that I don't rob him time to present the most interesting material. Mojtaba, your floor.
Great, thank you. Thank you very much indeed, Aubrey. So if I share my screen, okay. Can you see it?
Yes, we can.
You can. Oh, lovely. Okay, so I just go enlarge it. Okay, great, fine. First of all, thank you very much indeed for the invitation. It's been a great honor, and I'm delighted to see so many friends all over the globe who've come to listen to this talk. And as I said, I'm really very relieved the fact that I'm presenting something which is completely new, because otherwise, it would have been boring for some of you. So the work I'm presenting is based on the PhD work of Louis Scott, who is working with me and my colleagues, Antonia Borisova and Alan Burns. And this PhD work is actually supported by this Center for Doctoral Training in Particulate Products and Processes, which is an EPSRC, National Funding Body support. And the partner is AstraZeneca, and I should really say that I should thank them and express my great gratitude for allowing us to present this, because the time was really very short, and when I presented my slides to them, they did their best to clear it, and I'm really grateful. Otherwise, I would have had to drop this presentation and give you something which was an old one. So that is basically the background in here. Just to say a little bit about activities at Leeds, we can classify into two areas, milling and attrition. And in the milling area, we activities in spiral jet, vertical roller mills, shaker mills, GS3 disperser, and Sirocco and Eros S disperser. These are dispersers which are used for particle size analysis, and we basically have converted them to particle breakability testing. And we have published the work on how they break particles. On the attrition side, we have a project on attrition in fluidized bed and circulating beds, which is supported by Total of France and Institut Français du Pétrole, and also agitated filter bed dryers, attrition therein, which is supported by AbbVie in Chicago. So that's basically the activities in milling. Today I'm going to be focusing on spiral jet mills, and this is the content of the usual talk. So in here, this work is actually a continuation of a PhD project which was concluded in 2017, and that again was also supported by AstraZeneca. So the objective of this work is to analyze the effect of holdup, what is in the mill, and how that influences the particle profile, particle flow profile. So holdup is actually a dynamic parameter, which is based on the input of the feed material and also the breakage of the material and classification. However, in here, we do not look at the breakage for the reasons you see later on. So really, holdup is basically what we put into the system and vary that. We use CFD-DEM to simulate the mill. And the basis of the simulation is the AS50 spiral jet mill of Hosokawa Micro. So something about the background of a spiral jet mills. In contrast to mineral processing, and you're interested in ball mills, milling in pharmaceutical industry particularly, spiral jet mill is the equipment of choice because it has low contamination, particles mill each other, break each other, and of course it has low maintenance because it has no moving parts. It is mechanically very simple, but actually it is very complex from a size reduction process. Breakage is brought about interparticle and particle wall collisions, and that is again induced by an internal vortex, which is generated by gas jets. And breakage and classification occur simultaneously in the same space. So we have a fast shearing bed which forms as a result of the centrifugal field, and this shearing bed basically causes the breakage. So in this work, we analyze the fluid flow field and particle dynamics as a function of holdup without considering the size reduction. And the factors that I'll be looking at actually are not really that affected by size reduction, as you will see. So it's not a big handicap for the time being, and not including the size reduction in that process. So here is the spiral jet, a top view of it, which is on the one on the right-hand side, and a side view of a CAD drawing of this AS50. So basically, we have a manifold, as you see here, and we include the manifold in the fluid flow calculations because our work in the past has shown that if you include the manifold, the fluid flow pattern is slightly different from if you discard it. So we include the manifold for fluid flow. Then there are 4 nozzles inclined at an angle of around 40. And then we have also an injected nozzle. And this injected nozzle basically induces the flow of particles into the mill. So as you see here, this is the high pressure feed nozzle, and this is the cone in here, like that. This is the cone where the particles are introduced, and there is an induction of air in here, and that accelerates the particles and introduces it into the system here. So the pressure here is larger than the operating pressure that we have there. What you see here as the red area, this is actually the area that we introduce the particles. This is our particle generating factory. We do not use the funnel for introducing the particles in this simulation, but we simulate the fluid flow which is induced by the high velocity jet and also through the funnel, because that air induction is quite significant. So that's basically the design of the spiral jet. And in here, as I said, we look at the 50 millimeter grinding chamber. That is one of the small ones. Of course, there are larger sizes as well, but we haven't modeled those yet. We have 4 grinding nozzles at 40-degree angle, and the particles are fed from the top, although in this simulation, you will not have that. So we have an internal vortex, as you see here. Is there any delay, by the way, on my slide advancement?
No, it's fine. It's going okay.
Great, thank you. So we have this internal vortex, which is induced by these nozzles, the high pressure nozzles there. So the breakage is autogenous by impact and attrition. And in practice, when the particles become small enough, the radial component of fluid velocity entrains them out of the mill. So the product size is typically 5 to 20 micron in size, although we actually, in this simulation, we are not considering that, as I said. So in terms of the design features, as I said, the design is very simple, but it's got many operating variables. So you have basically 2 zones, a classification zone and a breakage zone near the wall. And these are affected by grinding pressure, feed rate, diameter and the height of the grinding chamber, nozzle size, nozzle number, nozzle angle, classification, diameter and height, and of course material properties. So we have really a large number of parameters, and in a way, in practice, once the mill is there, the only things which are changed are really the grinding pressure and the feed rate. And these two influence the holdup. So we have a dynamic holdup, which is influenced by these 2 parameters, and of course the rate at which the particles break. So we have many factors which influence the process. And of course, here we are only looking at the holdup and looking at the effect of holdup on fluid flow and particle flow patterns. Just to give you a little background in the field to acknowledge the contributions of previous workers. So I have classified into 2 areas. One is grinding nozzle and feed nozzle pressures, feed rate, grinding nozzle number, size, and angle. And I have listed the previous workers in here. Frank Muller and Polke from BASF, they have done a lot of work in that area. And also Katz and Kalman, and more recently, my previous PhD student, Selassie Dogbe, did work on that area as well. On the holdup, we have the work of Coulton and Rumpf, Kozawa, Muller, Lusak, and also this work. And I think Rumpf is really great. He's done everything. So in 1966, we had a PhD student, Coulton, who looked at the spiral jet mill, and they used triboluminescent dyes and water to look at the particle flow pattern. They speculated before they start that the breakage occurs in the front of the jet, but then later on they report that breakage of the particles occurs on the back side of the jet. I'm going to show you the front-hand side later on just to see what you mean. But it turns out that actually later on, when Lusak recently did some work, he used the particle image velocimetry, and then he found that actually the particle flow patterns is in agreement with original Room's speculation, but in disagreement with his findings. So he found, in fact, Lusak, he did a PhD in Essen, and he found that the particle breakage occurs primarily in front of the jet. So I have this work that is going to shed more light on what is going on in here. So in the CFD side, so we use Fluent for CFD, and basically the mesh side, as you see here, the particles, the device is meshed. I should first of all say that the design is not given by Mojtaba Micron for confidentiality reason. So, but we have one of these devices in our lab, so we took the dimensions ourselves and meshed it. So this is not exactly to the exact design of Mojtaba, but to our best ability is almost the same. So we use the Fluent for meshing, and these are the velocity vectors in the system. When we are doing particle fluid coupling, then of course the size of the mesh is important, and here we use the 40% guide for the cell volume to be occupied by the particles, following the recommendation by Norouzi. And we use turbulence model of K epsilon because it is faster, and also it gives reasonably good accuracy and is sufficient in terms of flow field, bearing in mind the mesh size and also the particle interactions. And we also allow fluid flow field to come to a steady state before we introduce the particles. So for DEM, for the discrete element side, we have four-way coupling, and this is very important because particles near the wall, they are in dense space because they are under centrifugal field. But eventually the fluid takes them to the middle of the mill, and then you have a lean phase. So we have a transformation from dense phase to lean phase, and also the fluid has the particles have got a certain momentum. So in a way, the four-way coupling is essential in that one. And there is still a lot of papers coming out in the literature doing two-way or one-way coupling, analyzing spiral jet mills, which in a way, the conclusions are inadequate. We use spherical drag laws for calculation of particle velocity. For the integration time step for particles, we use Rayleigh time steps of roughly 15 to 30%, and the CFD time step roughly 30 to 50 times of the Rayleigh time step. The pressure, we have used constant pressure in this simulation, although we have changed the pressure recently. So the feed pressure is 3.2, grinding pressure is 3 bar. These are bar G. And of course, these are low pressures as compared to practice, which is roughly 1 or 2 bar larger than this. But this is something that we have used previously, so it was a basis for comparison. So for the holdup, we changed the mass of particles in the system from 0.4 to 2 gram, and the corresponding numbers that we use in simulations are given there. And then for the particle size distribution, we give it in the table below. So roughly varying from 300 micron to 160. So these are basically the feed particle sizes, and the percentages on a weight basis are given at the right-hand side. So we come first of all to the fluid flow field. Of course, this fluid flow field is influenced by particles, remember that. And also ignore the manifold that feeds the fluid. So we start from the actual inner chamber in here, as you see here. And we have the results for 0.4 to 2 gram holdup. And in here, the velocity field, unfortunately, the numbers are too small to see, but they are from 0 in blue up to 100 meter per second, which is the red region. And basically, you can see the fluid flow field coming out of the jets and the way they move around. So these are the absolute magnitude of the fluid. So particle damping is indirectly reducing the velocity surrounding classifier. So if you compare the velocity here and there, you see that the introduction of 2 gram material there, it has dampened the fluid velocity significantly. Also jet length, you can see the jet length extends so long in here for 0.4 gram, and here it is very short in this system here. Velocity remains high in the classifier, roughly 70 meter per second is the velocity. So the red color is about 100 meter per second, and you can see again here they have very high velocity. So the velocity basically we have, if you like, a free vortex on the classifier. The velocity increases towards the center of the system. So basically, these are the fluid profile, which you can actually see and read a lot into it. But I would like to bring your attention to the definition of the sides of the jet, because this is something which is important. So we define the front side of the jet on this side, and that is the reason is that the particles are moving clockwise, and therefore they encounter this jet in here. So we call that one to be the front of the jet. And this is the back of the jet, and each jet would have obviously a tip, but that tip is not really that important because it's feeding into this region in here. So the way the particle grinding takes place is very important in this region, as you'll see later on. So here we have decoupled the tangential and radial components of the fluid velocity here. So we have, for the cases of 0.4 gram holdup and 2 gram holdup, and this is radial, these two are radial, and these two are tangential velocity components. And interestingly, you see that the radial velocity component increases as the holdup increases. So that's 0.4 gram, 2 gram, and you see here the red region here. So for this slide, basically we have the velocities which are from for the radial minus 70 to 20 meter per second. These are the velocities here, and as you see here, the radial velocity is red, which is orange red, which means that it is positive. So we have radially outward fluid here, which is because of the jet induction. So the jet moving the fluid in that direction, it induces and drags the air into it. So that's why you see radially positive values for the fluid for both cases to some extent, but to more extent for the large holdup. The tangential one provides really a fascinating trend in that you can see very high velocity. So the tangential velocity range is from minus 120 down to about 20, but most of it is actually orange, which is about 0. So what you see here is that in the region where we have particles moving, the tangential velocity of the particles, of the fluid, is very low. So what we have is very high velocity, which are clockwise in the jets, and then very low velocity near the walls. So as you see here, the tangential velocity is reduced while the radial velocity is increased as the holdup is increased. And of course, this has got implications on the classification, on the cut size, because the cut size is influenced by the ratio of tangential velocity to radial velocity of the particle squared. And therefore, one would expect that as the holdup increases, the particle size which comes out is increasing. So that's the fluid field. Now we move on to particles and particle flow patterns. Now particles basically move more over the walls. So I need to tell you how we calculate the particle flow pattern. So that's basically what you see here is the wall of the mill, and N1 is nozzle 1, N2 is the nozzle which is vertical there, and we analyze the particle velocity in slices. So you see here is a slice there, which is basically, this is the top view. So that slice goes right up to the top of the mill. So the Z plane, that is basically a Z plane. The Z axis is perpendicular to it. So this slice is about 8 particle diameter deep here. And it doesn't extend, well, it extends right to the center of the mill, because the mill is 50 millimeters, so that's to the center of it. However, you see later on that I only analyze and present the results up to about 12.5, because from this position onwards, there aren't many particles which are present. So we look at this average, moving average particles in this slide. However, for the next slide that I'm going to present, I'm not going to consider these slices, but a slice at 45 degrees. So a slice at that position, I'm going to present the particle velocities in that slide. And here it is, as a function of holdup. So what you see immediately is that the velocities, these are meter per second velocities, as a function of distance from the wall, and the maximum is about 12.5, and somewhere around 8 millimeters away from the wall, we have the maximum particle velocity. Interestingly, for 2 gram holdup, you see that there's a very shallow profile here, and that implies that for large holdups, the moving bed actually is moving as a plug, is not being sheared much. But from about 5 millimeters from the wall up to this maximum, that is where you have the velocity gradient. So that is where the bed is being sheared, and that's where you would get particle breakage. So that's for 2, and then I go to the lowest one, which is 0.4 gram. As you see here, 0.4 gram, immediately you get the shearing, because there is hardly any depth of the bed in that system. So you have a velocity gradient right to the maximum. And the other mass loadings vary in that way. So 1.6 and 2 still have some plug flow arrangement in the system. So that's basically the profile of the particle velocity in that slice, which is based on a moving average of 30 points. So what happens actually in terms of this is the top view of the particles for the whole of the bed of the jet, of the mill. So we start from 0.4 gram up to the maximum of 2 gram holdup, and as you see here, the 0.4 gram, you have very high velocities. These are because of the jets. And then you have much lower velocities for 2 gram holdup. I'll pick up this one, which is it illustrates that is 1.2 gram. What is going on in here? So the jet is, one of the jet is here, and the particles which are coming here, they actually slow down by the high velocity jet here. So they pile up here. That's why the velocity is relatively small and is the blue region in here. The jet, which is around here, it actually projects the particles out of the bed surface and impacts them in this region. So near the bed surface, there is a lot of collisions at high velocity, and that goes on in the whole system around for all the jets. Bear in mind that the system is not exactly symmetrical, because we have a feed nozzle which is feeding fluid at 3.2 bar G into the system somewhere around here. But overall, that is the contour plot of particle velocity on a Z-plane as a function of holdup, showing significant reduction in velocity as the holdup is increased. In the next slide, which I have a video of it, I'll show you a video of particle velocity and particle population in this slide, rather, but the slice moving from this position at 5 degree intervals from N1 to N2. And that way you see a video of what goes on along the radial direction in terms of population of the particles, and also in terms of particle velocity, because we have color-coded the particle velocity. And here is the video. So you see that the bed fluctuates because of the jets. Once the jet penetrates, you can see somewhere in the middle an empty area here. By and large, you have very small velocities in here, but at the bed surface, you have roughly about 10 meters per second, very dark red region in here, where you have a high velocity. So here, look at, it's not really extending beyond 12.5 millimeter from the wall. We have hardly any particles. So we have a dense bed of material which is moving along the bed, fluctuating, being disturbed by the jet. So as you move from one jet to the other, you see that this area appears here, and that is the presence of the jet penetrating into the bed of material, splashing the particles out of it, and then the particles land near the next jet into the system. So the interesting point is that the particles are uniformly distributed over the height of the mill. Also, the base of the mill is slightly inclined by design, so that is why you see that one inclined in that way. So basically, as I said, we have rather flat velocity profile in here because they are all blue, moving very slowly, while at the surface we have significant fluctuation in the bed due to the jet action. So we now come to the kinetic energy calculation. So particular advantage of DEM is that you can calculate the kinetic energy. So here we have the temporal variation of the kinetic energy of the system. So that's basically the summation of half mv squared. That's of all the particles. And something surprising happens here. If you look at 0.4 to 2 gram holdup, you see that they all have an asymptotic level around 7 joules. And that was really surprising to us initially. So feeding is complete at about 0.1 seconds. So this profile from here to here is on non-steady state behavior because of feeding, but from there on the system comes to a steady state, and you see that all of them approach to about 7 joules. So overall, what is happening is that what we are reporting is that the total energy of the system is constant, irrespective of the holdup. There are implications on that, and that's that particle velocity is decreasing. As the particle number increases, the collision velocity, so the system is complicated because the collision frequency is changing, the collision velocity is changing, a lot of things are changing, but overall, the total energy dissipated is constant. So in the next 3 slides, I have the actual profiles of the collision intensity, collision frequency, and the total kinetic energy. This one is the collision energy. And for collision energy intensity, for 0.4, 1.2, and 2 gram holdup, these are spatial distributions of dissipated energy. And basically, what you see here is that collisions in front of the jet and in the shearing region have most of the dissipated energy. And of course, particles enter in the bed. So basically, if you, for example, see this jet here, so you have a little bit of red region here showing that, but the particles which have been splashed out land up here. So the collision is in front of the jet. So that's one of the jets, and that's where the collision is. The same applies here. Particles which are ejected by the jet here land up in here, pile up in front of this jet, and that's where you get the largest collision energy. So interestingly, particles in the deepest layer do not experience high intensity collisions. Only what goes on by particles being splashed out of the jet, landing in front of the jet near the next nozzle, and of course the particles which are being on the surface. So that's the collision intensity. That's collision frequency. So again, we have for the same loadings, and in here we have the collision frequency summed up for the whole time. So it goes a very large number of collision frequencies. what you see here is that actually the 0.4 doesn't have much collision frequency. But in here, you have enormous number of collision frequencies. You see later on that the velocity is small, so you have large collisions, small velocity. Here, you have a very small number of collisions, but very high velocity. So particle collision frequency is highest on the bed surface. So around here, as you see here, these are the bed surface, and that's where you have highest collision frequency. So shearing layers rapidly bring the particles in and out of the contact, and particles re-entering the bed increase the recorded number of collisions. Actually, interestingly, few collisions occur along the jet itself, because of course the jet splashes the particles out. So within the jet, the particles are in lean phase and they are being accelerated. So there is not much collision. And here is the last set of slide on the dissipated energy within the milling chair. So we have here contour of the spatial distribution of the dissipated energy for these three mass loadings. And as you see here, you can clearly see where energy is being dissipated. It's along the bed surface due to the high shear and high intensity collisions, and where the particles are re-entering the bed in here. So you can see. So we have, for each cases, we have a particle along the front of the jet, and also on the pilot rear, where this jet is shooting them here, they pile up here. The bed is moving and it's been stopped by changing the direction of the particle in here, because the jets got the energy are doing that. So these observations actually now are in contrast to the findings of Courtin and Rumpf, but they are in agreement with Lusak in 2019, where he did the velocimetry of the system. So, conclusions. The amount of material held in the bed affects the fluid velocity surrounding the classifier. Large holdups lead to less energetic collisions. The kinetic energy of the particle system remains constant. We don't know exactly why, but we speculate that that is because the total fluid power input to the system is constant. So Luis right now is actually looking at changing the fluid power by changing the pressure of the system and see what we get there. But that is at the moment our speculation. But there are other reasons, there are other reasons where the total energy, kinetic energy of the system is constant. Energy dissipation occurs primarily in the top layers of the bed due to shearing and particles re-entering the bed. And high energy dissipation is also found in front of each jet, as particles are suddenly accelerated in a different direction and increase their relative collision frequency. That's it, really. I would like to acknowledge AstraZeneca, who are partners in this project, and the coordination of Ian Gabbard and Catherine Hallam from their all our product development and pharmaceutical technology. I really owe a great gratitude to both of them, who managed to get clearance almost within a day for this presentation. So I owe much to them in being able to deliver this talk. And that's it. Thank you very much for your attention.
Thank you very much, Mojtaba. I'm sure you can hear the hands clapping in the background. That was a very stirring presentation and a very good insight into this meeting technology. Thank you. We can take a number of questions, just a discussion. We have time for that. So to facilitate the discussion, you can either use the raise hand in the system, or just switch on your video, then we can see you at the top. Okay. Any questions for Mojtaba?
I might ask one.
Yeah.
That was really interesting. I was fascinated how square the flow is inside because of the flow. I didn't expect that. But the get shared out to more and more particles is really fascinating, because that means your specific energy, which I was busy starting to calculate, maybe Marcelo's already calculated, is a direct function of the loading you put in, which means you would then tune your specific energy by the loading. It would never have occurred to me. I think that's a really interesting outcome. It's more comment, but it's just really interesting in the control.
Yeah, we thought a lot about it, Malcolm. I mean, how come it's impossible to think about initially that the total dissipated energy is constant irrespective of mass holding? But then of course, we have used 3.2 bar G of fluid nozzle, the feed nozzle, and 3 bar G of grinding nozzle pressures. So the total flow rate and the input power for the fluid is constant.
It's constant,
And
yeah.
then presumably the particles, whatever the loading they have, they reach to that. In other words, one could say the other way around, that is, fluid power is far more than what is required to get the particles to what they are there.
Yes.
Thank you very much. Any question? Any other questions for?
Yes, if I may.
Yeah, Marcelo.
For people getting warm up. Yes, excellent talk, Mojtaba. And actually, just taking a ride on Malcolm's question that you didn't, of course, present experimental results, but you have plenty of those in your lab, I know, for testing this spiral jet mill. So, for instance, how would actually attrition look like when you actually change the loading? Because given this total power, there is going to be, of course, a more reduced attrition as you increase the loading. Have you tried to use your attrition model to reconcile this? Because I believe you didn't end up mentioning why you didn't include breakage, but of course, four-way coupling is plenty. But maybe as a post-processing stage, you would have tried or be thinking about trying your attrition model, and the likely response will be, of course, reduced breakage as you increase loading because you're dispersing the energy in more particles. Can you comment on that, please?
Yeah, they're great points you raised, and it's got two fronts: experimental and simulation. On the experimental side, actually, the practice on spiral jet milling indicates that as you increase the mass loading, the particle breakage increases significantly. And they say that there's actually an optimum condition for operation as a result of holdup. But that is basically on the practical side where we talk to practitioners. We have looked at the particle breakage experimentally, but we haven't. What we should really do is to present it in terms of energy utilization, and that one we haven't done yet. But it's something that we have. We did the experimental work actually in collaboration with AstraZeneca using their two mills, 50 AS and also 100 AS, and but we haven't yet analyzed those in terms of energy utilization. On the stimulation side, Louis actually tried to load our model into it so that we can look at the attrition. And for some reason, Marcelo, the code crashes. At the moment, we don't know what is going on. But once we put our model into the system, it becomes very slow and also it crashes. So this is something that we are working on. At the same time, we are also working on using clumped sphere models, rather bonded models, so that we use, for example, the bonded models of Piccioni and Kondo to look at bond the particles so that we have aggregates and see how aggregates would break down. In that way, the sphericity of the shape of the primary components is maintained, although you may have fragments. But this is something that, again, Louis is doing right now. So there's more to present, comes later.
Can I just take this opportunity to follow on Marcelo's question? You did show in the presentation that there are instances where you have a very high intensity of particles and low frequency. Is there a way you can promote both high intensity and high frequency, because that's where breakage would be promoted in the device?
I suppose that's can be manipulated by changing the feed rate. So in that case, hold up. Yeah, you can do that. That's why in practice, I hear from the colleagues Pushkar Martin that they say there's always an optimum hold up, and that's they believe, and that is I think what where you say. But the interesting point is that the system is coupled, grinding and classification is coupled, and they influence each other. So in a way, once you increase the hold up, you have more breakage, and then you have more entrainment. The cut size changes. So it's really a fascinating system for analysis.
Yeah, thank you. We have time for more questions. Please, any further questions for Magnus?
Yes, thank you for a very interesting talk. I was also recognizing the square pattern, and then I was thinking the circumference is circular. So what is the reason for that, or could that be varied, maybe to have a wavy outer shell? Or
so, well, I think to some extent, first of all, we have 4 nozzles which are fixed at 90-degree interval. And these nozzles are at 40-degree angle with respect to the tangent to the wall, okay? So the overall, and at high velocity, so you have basically some sort of a square of high velocity jet. But overall, I think the square arrangement also to some extent is artifact of the coloring of what we are showing, okay? So in a way, it's not exactly the position of the particles on a top view, because of course you saw from the video the way the bed fluctuates up and down because of the jets. So you have the jets ejecting particles from the dense space into the region. This ejection is along the jet axis. So that produces the rectangular or the square pattern of the thing. But overall, near the wall, the particles, of course, are going round in a tangential way. But we don't see that because this is the way coloring has been done. We could maybe do a better video presentation of the actual dense bed of particles moving to show exactly how it looks like.
There is a question in the chat from Andre. It says the RSM turbulent model does not present any improvements in the accuracy of the CFD prediction in such a vortex flow, and the K epsilon model set as a dispersed or mixture model doesn't present any difference. Is there any needs for careful setup of preconditioners to reach stability?
Okay. I'll actually later on I want to pass on to Luis to answer that, because he did both RSM and also the K epsilon model. Actually, we also have Alan Burns online, so Alan could better answer everything. But we have tried both. The point to bear in mind is that we are limited by the mesh size, because we cannot have a mesh which is smaller than the particle. Then the whole system does not work anymore. So we are limited by that. And I'm not sure about in this case, but in some of the previous cases that we had on spiral jet milling, we actually didn't come to a steady state with the low residuals for the fluid when we have particles in the system. We had to be satisfied with what that mesh would give us, you see. So, but anyway, I just pass on to Luis to say if he could say something about his work on RSM. Luis, can you say something?
Yeah, and thank you for presenting, Mojtaba. It was really, really good to hear my own work being presented by someone else for the first time. Thank you. Yeah, so to answer that question, I originally did the K epsilon RSM and K omega model all trialed when I originally did like the CFD study. and there was no real difference between the flow fields, as Mojtaba said, due to the particle size that's being used. We're limited by how small we can take the mesh size. So you lose some resolution of the fluid field anyway. So when you compare the two, there isn't much of a difference between the fluid fields for any of the models. So realistically, it becomes a problem of time. To solve one of the simulations using RSM, it can take up to 2 weeks, whereas using the K omega model, it's something around maybe K epsilon model, it's something around maybe a week or just less, depending on the particle size. For this study, the smallest particle was, I think it was 80 micron. So already you're talking below 1 times 10 to the 6 as a time step in EDEM. So you can only really try to push the time step up in K omega, in Fluent up to maybe just below 1 times 10 to the 5. So if you want to realistically get a good chunk of time where you can actually see actual results, then it's not unfeasible to do it with RSM, but it's so much easier, and you can achieve a lot more using the K epsilon model. Is that?
Thank you very much, Luis. Are there any further questions? We have a few minutes for. Yes, Hoga.
Yeah, if I might come in at this point. First of all, Mojtaba, thank you very much for the very interesting presentation. For me, are you aware about the works which are done by Wolfgang Bucher in Nuremberg? I've seen some quite interesting experimental work by one of his PhD students, maybe 2 or 3 years ago. He essentially injected aluminum spheres, same size, around 100 microns, in a quartz bed in a jet mill, a cross jet mill. And after exposing the alumina balls, same size and density, for a certain time to the operation of the mill, he investigated the balls and the dents, which were the imprints of the particle collisions into the spheres. And then by finite element methods, he calculated the energy, he back-calculated the energy of the collision. And it was quite interesting that actually the energy he calculated, he back-calculated, was resulting or was pointing to a collision speed of somewhere in the range between 15 and 20 meters per second, while the assumed collision speed was 100 meters per second or more. So which could be a hint that essentially the attrition or the mechanism is not so much a collision in the mill or a high-speed collision and the resulting breakage of the particles, but more an attrition. So essentially it's more like a stirred media mill than really a collision. So what we assume usually shooting the particle against each other. It's more that the particles are reduced in size by sheer friction. That was quite interesting, essentially.
Thank you very much, Volker. I was aware of that work, but I don't think Luis is aware of it. So it's great that you mentioned it, and we need to go back to study it in more depth. One thing when we do the simulation is that because actually we cannot use very small particles, some of the experimental work that's been reported in the literature, we cannot use those for comparison. So that's basically a handicap of discrete element method calculations, that it cannot go to very fine particles as they exist in a spiral jet mill. But it's very fascinating on what you say there. I fully agree. The collisions are such that attrition could predominate, but that really very much depends on the material properties of the particle. So if you have something which is prone to attrition, of course it would undergo attrition. But on the other hand, if you have something which is not prone to attrition, then eventually it would fragment. But one point is the frequency of collision would also give rise to weakening of the particle. So that weakening, in a way, is a second mechanism which comes into effect. Initially, you have surface damage, but then later on, that surface damage creates micro cracks, and these micro cracks can propagate and fragment the particles. So the interaction of material properties with collision intensity is something which needs yet to be modeled by DEM, taking account of material properties. Mehtab's got a question. Yeah, Mehtab.
I just asked 2 quick questions. So one of them, so based on the presentation that you gave, so do you think there is a possibility that depending on the holdup, we switch from impact breakage to shear breakage? Because of course the impact velocities, they go down, but you haven't analyzed the level of shearing the bed has depending on the holdup. Do you think that is possible? I mean, it's back to the previous comment. And the other one is the comment that Marcelo made on the particle breakage. So do you think increasing the particle size distribution in the simulation in order to somehow to interpret the particle breakage, having smaller size particles in the simulation would shed some light on the change in the flow patterns and etc.? I think that if having the breakage is not possible because it's already an extensive simulation, but maybe just artificially changing the size distribution in order to show you had some sort of breakage, and what is the effect of that size distribution in the simulation?
Okay, yeah, good 2 questions. The first one, the simulations show that actually particle wall impact is not influential. So it's really particle collisions. And again, what do we mean by shearing? Because we don't have, in this case, like a shear cell where the particles are loaded and sheared. That's not, the simulations don't show that. So you have basically shearing caused by rapid gradient of particle velocity induced by gas. So towards the bed surface, you have more or less a dilute collisional regime, but there is a strong velocity gradient across that because of the centrifugal field. So you have that process. So really, is a shear caused by collisional effect. That is the mechanism there, and that is interparticle rather than the particle wall. Coming to your second question on the particle size distribution, I think it's difficult to answer exactly how it's going to pan out. The distribution we have taken is not that wide. The question is, what is the role of very fine particles in the system and where they are going to end up? So if you look at the centrifugal field, I speculate that the large particles are going to be near the wall going round. The fluid jets are going to splash the particles out of the bed. So there is going to be prevalence of fine particles on the bed surface. So you have a segregated bed. I think Selassie has done that in his, but to be honest, I can't recall the result of his work. But I speculate that you have a segregated bed with the surface being predominantly fine powders, but these powders are not yet ready to leave the bed because the centrifugal field is holding them back. It's only when the drag exceeds the centrifugal forces that they're going to be entrained into the system. Now, with Selassie's work, again, what we found that the cut size of the bed, because we went right down to 2 micron in his simulations, we found that the cut size of the bed was around micron size. And that has really still has baffled us, because in practice, you get particle size distribution varying from micron sizes up to a few tens of microns. But when we did the CFD simulation and looked at the particles, they were not coming out of the bed. they were not coming to this classification zone, or no, they were coming to classification zone, but they were being rejected by centrifugal field. So we then abandoned that and said, okay, let's just look at particles, doing Lagrangian calculation of particles for micron size range to look at the separation efficiency, classification efficiency. So we did a full calculation of the classification curve, and what we found that actually particle cut size was around 1 micron on the calculation, and that to the date is baffling me, because that is not in agreement with our practical observation.
Thank you very much, Mojtaba. I think you can see this is a fiery topic. We can go on the whole day. You've actually opened up a very interesting subject. We would like to thank you for stepping in at short notice to give such a stirring presentation. And this is really good work. And to everyone, we hold this seminar every month, every last Thursday of the month. So you can mark this in your diary, and we, as a scientific engagement, will have similar topics in the future. I now just hand over to Marcelo if he's here to close our seminar for us.
Thanks, Aubrey, and thank you very much, Mojtaba, for the fantastic seminar. And indeed, the invitation is open to the group here that definitely became more varied with Mojtaba's presentation, spreading beyond the mirror processing comminution that we're accustomed to. So we thank everyone for being here, and Mojtaba again, and looking forward to next month. You'll be announced in a couple of weeks. So,
Marcelo, I should say I would like to thank you for the invitation. It was really great pleasure to see you all, and that was really fantastic for it. And also, I look forward to a day where we can all get together and we beat this pandemic, and I'll have a jolly together in a meeting face to face. Thank you very much indeed. All the best.
Thank you. Thank you, Mojtaba.
Okay, goodbye, everyone.
Bye. Bye.
Bye then.
Bye.